Hi, welcome to what this time I really do hope is the last screencast of the year. So this is on Bernoulli's principle. This is the culmination of our fluid units. There's just these four lessons. So let's just jump in on this. Bernoulli's principle is something that a lot of you have probably already heard about. You often hear it about it in the context of airplanes or curveballs, things like that. So let's just talk about this briefly. Okay, so the basic principle here is this, that if I have a fluid flowing through a closed environment, what I'm going to find is this, that when the speed is low, the pressure is high, but when it picks up speed and the speed increases, there will be a subsequent decrease in pressure. So basically, the faster the fluid is moving, the lower the pressure. The slower the fluid is moving, the higher the pressure. Pretty simple idea, but obviously it's going to be a little more complicated than that. But let's just take a look at some of the implications. So the most common one that is presented is the idea of an airplane wing. So if you look at bird wings, airplane wings, you'll find they have what's called an airfoil design. Basically, what that means is that if this is the front of the airplane, the wing is shaped like this with a top curvature and the bottom is fairly flat. And so as the airplane moves through the air, the relative speed of a particle going under the wing would go this distance, so a shorter distance in the same amount of time that this one travels. So the particle going over the top is going to, the particles aren't actually going anywhere, but relative to the plane, particle A went a greater distance in the same amount of time, so it had a higher velocity. So what we find is high velocity, low pressure on top, lower velocity, higher pressure below, and that pressure difference is what lifts the airplane. So that's something it gets talked about a lot. To be honest, they may ask you about that on the AP test, and it is cool. But I really want you to understand at a more physics level what Bernoulli's principle is all about. All right, so a better way to think of Bernoulli's principle is another way of stating conservation of energy. So really what we're saying is, instead of saying when the speed is low, the pressure is high, and when the speed is high, the pressure is low, instead let's just say when the kinetic energy is low, there's a form of potential energy that's derived from pressure that is high. And therefore, when the kinetic energy, the speed, is high, that potential energy that is derived from pressure will therefore diminish by a corresponding amount. That's the idea of Bernoulli's principle in a nutshell. So let's get our minds wrapped around this idea of how it is that pressure is a form of potential energy. And about the best way I can do it. Now, generally speaking, on the AP test, you will only be dealing with ideal fluids, which are incompressible. That means that the particles can't get any closer together. It's true for those two. However, it is easier to think of it in terms of a compressible gas. I think it's just we have more innate experience with this. Let me just try this here. So here's what we've got. Imagine I have a container here that is open to the atmosphere. Now remember, gauge pressure is basically just measuring how far above or below normal atmospheric pressure you've got. So if this is open, it's going to be at atmospheric pressure, not above or below it. So my gauge is going to read 0. I'm not above or below atmospheric pressure. Now what I'm going to do is I'm going to force air into this container. So I'm basically doing work. I am applying a force across the distance, and I'm pushing air into here. And as I do, this now has greater pressure than atmospheric, so the gauge pressure goes up. Then I seal the door, okay, the valve, okay? That pressure is high in there, and it's pushing outward in all directions. And so this pressure I see here that I read on the gauge is basically a form of potential energy. Because look at this. Once I open that gauge, what's going to happen? This pressure is going to push particles out of here, giving them kinetic energy. In that sense, pressure is a form of potential energy because it can cause particles to gain kinetic energy. So we often refer to this then as pressure energy, and that's a little bit complicated. So basically, in most cases, pressure energy just means gauge pressure, okay? And gauge pressure often just means hydrostatic pressure, but not necessarily. So bottom line is we're going to use pressure and pressure energy, well, gauge pressure and pressure energy somewhat interchangeably in this unit here. Now, listen, this slide here, don't sweat it. The only reason I'm putting it in here is so that you can see that basically what we're doing here is we're talking in terms of per unit volume, which is really hard to wrap your head around, and you don't really have to in most cases. I just want to show you how it is we derive these ideas here, okay? So the idea is this. We know now that pressure is equal force over volume, P equals F over A, so therefore I can rearrange it and say force is equal to pressure times area, all right? Now work which is energy, the energy added to or taken from a system, is equal to force times distance. Okay. Now, force, we said we can substitute with pressure times area. So I'm going to put PA here. So now I have W pad. Okay. Now, but the distance it travels, well, so if I have an area and I have a distance, that's a volume. So I can take A and D and just turn it into V. So I could say, well, work equals pressure times volume. Now, pressure energy is this, is pressure times volume, but I often want to talk about it per unit volume because when we're dealing with moving fluids, it's easier to think about that than actual how much mass is moving. So we just do it per unit volume. So if I divide this by V to get per unit volume, I just get P. Mr. Sanders, why did you go all this just to come up with P again? I know, but that's the idea. Now, let's do the same thing with kinetic energy. So kinetic energy is the energy a fluid has because of motion. I'm sure that's not surprising to you. As always, K is equal to 1/2 mv squared. Now, we're just going to say, well, what is it per unit volume? So if I just take this expression and I divide it by kinetic energy per unit volume, would be 1/2 mv squared per unit volume. But now look what happens. I have m over v, and m over v is just density. So I could say that the kinetic energy per unit volume, that K that I'm going to use in this equation, is just 1/2 density velocity squared. Okay, so now I have two things I'm going to be using in Bernoulli's principle. I have pressure energy per unit volume, P, and I have kinetic energy per unit volume, which is going to be 1/2 rho times velocity squared. So now let's just lay it out. This is just the same thing. This is the same thing as saying UG plus K equals UG plus K. That's all it's saying. But our U, in this case, is gauge pressure, which is also pressure energy per unit volume. This is my initial kinetic energy per unit volume. And so what I have before is what I have afterwards is just a statement of energy conservation, assuming that there is no, friction in the system or compression happening, so that the total mechanical energy of this fluid system remains constant. It's just another statement of something we've been working with all year. Okay, so let's kind of put it into practice. So I'm going to use numbers here instead of just variables, but let's just try this here. It works a little bit easier for me to just talk about it here. So let's just say I have a pipe that goes from a large diameter to a small diameter pipe. We know from the continuity equation that as I go into this narrow one, it's going to speed up. So let's just say in this case, since this was 1/2 the radius, that means I have 4 times the speed. So therefore, it's going to go from 4 meters per second to 16 meters per second. So I just want to know, what would I expect to see on this gauge pressure? Well, this is going faster, so I should see something less here. So what I have here is 2,000 kPa, 200,000 kPa, and 4 meters per second. So let's just go into our Bernoulli's equation. So here is my pressure energy per unit volume, my p-value, okay, which is just what I get straight off my gauge. That is my pressure energy. Plus 1/2 the density of the fluid, which we're told here the density of the fluid. Look at this. I didn't give you that. So, well, what the heck? Okay. Oh, so I guess it's just water is why that is. Okay. So water has a density of 1,000 kilograms per cubic meter. It's traveling at 4 meters per second squared. So when I solve this, you see, I'm going to end up getting 80,000 pascals, or 80 kPa, which is significantly less than this 200 that I started with. As this goes faster, it's going to go slower, and I can calculate just using this equation here. A fairly classic type of problem that you get on the AP test, and it's just a good one that physics books use to try to help you get an idea of it, is imagine if we have this like a wooden barrel, let's just say, and it's got water filled in it, and I'm going to shoot a bullet at it, like in a Western movie, okay? Yeehaw! So what I've got here is I shoot it so that the bullet hits at this depth h, okay? So now when I go in here, water's going to flow out, and what we want to know is we want to figure out what the velocity is, and usually what they're going to do, and what I'm going to do, is we're going to combine it with two-dimensional kinematics and have you predict like where it's going to land on the floor, somehow take into account the fact that it's accelerating downwards as it travels horizontally at constant speed. You should be able to do this by now. But for right now, we're just going to focus on the velocity at which it comes out. So look, I've got basically a hydrostatic pressure here. Now, in this case, the gauge pressure, if I took a gauge at the surface, it doesn't count atmospheric, so I'd read 0, and when I got down to here, it'd tell me what my gauge pressure is, which is basically what my pressure energy is here, which is what I'm going to use in Bernoulli's equation. So it's just the hydrostatic pressure, as long as if it's open to the atmosphere on both sides, which it is. Okay, so let's figure out what the velocity is going to be as it comes out of there. And now we're just going to do it with variables, okay? So I'm just going to say, I'm going to take Bernoulli's equation, and for the pressure, it's just going to be the hydrostatic pressure, which is going to be rho gh. But there's no velocity here, so the kinetic energy is 0. When it comes out of here, it doesn't have any hydrostatic pressure anymore, right? The hydrostatic pressure went to 0. It's not at any depth anymore, so it's going to have some kinetic energy. And look, we get what we always get when we do this conservation of potential and kinetic. We get our old friend root 2 GH. How about that? It's just conservation of energy all over again. All right, well, let's try just changing things up a little bit, okay? What if I put some pressure downwards on that? I put like this sort of a plunger type system, like it's like a seal, and I can push down on it. And so I'm going to push down on such that this gauge, so if I had this gauge here without this on it reads P, but now I push down with enough force, now it says 2P. So it's not just my hydrostatic pressure is my point here. The pressure energy in here would be double what it was before because I'm putting more force on it. I'm giving it more pressure. So clearly it's going to come out of there faster. Why? Because there's more pressure energy. There's twice as much pressure energy. So I'm going to say, well, basically I have twice as much since my initial pressure energy was the hydrostatic pressure. It's just double that. And I use the same equation, and now I'm going to get square root 4GH, which basically means it went up by a factor of root 2, which is what you would expect. Okay, so this, in which case this is going to go out, comes out root 2 faster and go root 2 times further before it hits the floor. What about if I have it where as time goes by, and this is a common experience, if you have a hole in something, as time goes by and it drains, the water comes out at a lower velocity. Why? Well, because the pressure energy is changing, the gauge pressure is changing. So I start off, I have a gauge pressure of rho GH, which is going to make it come out of here, as we just saw in our 2 slides ago. It's going to come out here at root 2 GH when I apply Bernoulli's equation. So if I look at this, here's what this tells me. It tells me that velocity is proportional to root h. And now h, as it drained, it was here, is now half the height of that it was, half the depth. So therefore, I would just say, well, if v is proportional to root h, then I'm going to end up with 1 over root 2 velocity when I get to here. It's just the same physics we've been doing all over again. We just have to, we use rho a lot. That's all. Okay. All right. Now this one, I might regret telling you this, but I just think it's kind of cool. Okay. So look at this. In most of the cases you're ever going to get, they're going to give you things, at least for this type of problem, like the bullet in the barrel kind of thing. It's going to be open to the atmosphere. So this is what we just saw, right? So when it gets to half the height as it drains, it's going to come out at 1 over root 2v. But what if it was a sealed container, like a 2-liter bottle? Okay. Well, now something interesting happens, and that's because as it drains, this volume gets bigger. And you probably remember from chemistry, I believe this one was this Charles' law, I think it is? I forget my laws, but basically what it says is as the volume gets bigger, the pressure gets smaller. They're inversely proportional. Let's just say that in doing this, the volume got twice as big. Well, the atmospheric pressure inside this container is now half of what it was. So if I had a gauge here, it's not just half of what it was, it's a quarter of what it was because I have half as much atmospheric pressure pushing down on it. And maybe not just a quarter, but it's going to be less for sure. Okay, so it's not going to come out as fast because, and another way of thinking about it is the atmospheric pressure here is only 50 kPa, whereas the atmospheric pressure pushing it back in is 100 kPa. Where over here it was 100 and 100 and just canceled out. In this case, it wouldn't cancel out. And if they were to ask you about that, it wouldn't be a calculation problem. It would be just do you understand? It'd be like a communicating understanding idea. And the idea would be that the gauge pressure would be reduced because the atmospheric pressure is reduced. Okay, now what we were talking about before was called Bernoulli's principle. Bernoulli's equation also takes into account gravitational potential energy. So this would be what the full expression would look like. Okay, so basically, you know how you used to have like K plus US plus U plus UG? Well, instead of US, it's just pressure energy. Okay, so I have pressure energy plus kinetic energy plus UG, but UG is going to be expressed as gravitational potential energy per unit volume. So it's going to be uh, rho GH. Okay, and now I have pressure energy. And now you might go, well, Mr. Simpson, I thought this is the same thing as this. Well, it was in that barrel example, but a lot of times what we're dealing with is pipes. So if I have a pipe, if there's more pressure on one side of the pipe than there is on the other side of the pipe, it's going to cause water to flow from high pressure to low pressure. All right, so this pressure energy doesn't have to be hydrostatic pressure. It could be, like pump pressure. Okay, so just if there's pressure in the pipe, it's going to push things and give them kinetic energy. So this is our full expression here. Let's just try to use it. So this is the hardest it's going to get in this unit. You're ready for it. Let's do it. Let's go. So here's what I've got. Water's flowing through a wide pipe at 2 meters per second. Okay, and I don't know what the gauge pressure is here. All right. Now what's going to happen is it's going to go uphill and the pipe is going to narrow. So now it's going at 4 meters per second. And so up here, I know that, and in doing so, it went up a height of 2.5 meters, whereas before it was 0.5 meters. So I have a gain of 2 meters here. So the center of this pipe is 2 meters higher here than it is here. And I know I have a gauge reading of 100 kPa. So if the question is, what is the value of the gauge pressure here? Let's just try it. I'm solving for this. What is the gauge pressure, the pressure energy down here? Well, I know that I'm going to use this equation here. I'm solving for this. It's water, so it has a density of 1,000. So I'm just going to take this, substitute in the density of water and the velocity of the fluid. I'm going to call this height here zero potential energy like I normally do, okay, for the low point. So it has no gravitational potential energy. Now, as it moves uphill, I now know I have 100 kPa, which is 100,000 pascals. Got to mind that, okay? I can't use kPas and these other units. So I have to convert it to pascals because that's newtons per square meter, all right? And then I just say, well, and then 1/2 of my density times this velocity squared, plus, now how much potential energy did I gain? I gained rho, which is 1,000, times g times 2, because that's the difference in height between here and here. And when I solve it, I see that this pressure reading down here should be 126 kPa, which is more than what it is here, which makes sense because I got to push it up and make it move. All right. So another one would be like, okay, so let's say I have jet fuel that has this density here flowing through a pipe so a lot of times what they'll do is they'll give you a scenario where you've got to figure out what the velocity change is by using the continuity equation. So I see that this one here has half the diameter of this one there and this side here, so therefore half the radius, which means that I have 4 times the velocity, because remember it's area, velocity times area equals velocity times area, and so therefore this area is 1/4 of this area. So if I want to solve it, I would just say, okay, so I'm going to use my continuity equation to figure out what the velocity is here. It's got to be 4 times what it is here, so it's going 20. Okay, because it's half the radius. So now I'm just going to use this. I don't have to use the full equation here because there's no change in height. And usually College Board will do that. They'll usually give you a straight pipe and make it very clear that you're not changing height, so you don't have to worry about the rho GH part. So I'm just going to say pressure A times this kinetic energy is equal to pressure B times this one. And now I just substitute in, so I know that this pressure reading was 200,000 or 200 kPa. I know that this was my density. Now, you got to remember here that 0.8 grams per milliliter, if you multiply grams per milliliter or grams per cubic centimeter times 1,000, that gives you kilograms per cubic meter. And you've got to be working in kilograms per cubic meter to do this. So you've got to make that conversion, okay? times velocity squared is going to equal this new one, which I'm trying to solve for. And here's my density, and here's my new velocity. And I see that it would be 50,000. So whereas this one was 200,000, P2. This one was 200. Okay, I thought, why is it bigger? It's not bigger, it's smaller. Okay, this one got smaller, as we would anticipate it to do. That's it, people. We're going to practice this. We'll be done. Woo! That was AP Physics 1. You rocked it. Now we just got to get you ready for the AP test once you get past the test on this. Okay, see you later. Let me figure out how to turn this off. Haven't done these in a long time.